So my name is Eric Boyer. I'm from agency, French agency. I'm involved in EUPEX, but I will not present you exactly outcomes from EUPEX, but more what is going on in the context of Exascale from now to the next few years. There are some trends which are really changing the landscape of that. So the agenda is, okay, what are now the defining constraints of Exascale class system from now and in the future? I will just try to explain what is the efficiency and power trends that explain the constraint we are encountering. And then how could we address them by addressing energy efficiency? It is a systemic challenge. And yes, my colleagues showed some part of the brick. I will show you. And then afterwards, a conclusion. I hope somehow optimistic, even though the context is a bit producing some worrying. So, what are the defining constraints? So, energy efficiency is becoming definitely a key constraint for Exascale class system. Power limits, operational cost, environmental impact are becoming pregnant. Energy cost and availability of energy and components are becoming limiting factors. Okay, and sustainability is no part of the HPC procurement. It's mandatory. So I will try to use something which is an outdated tool. Top 500 will no longer represent what is the potential of an Exascale class system. Exa 10 at the 18 is related to what FP64 with the old-fashioned HPL is able to handle. Well, the thing is, behind the FP64, a lot of potential exists, but still, it is quite interesting to see how the trend is going. In the 90s, between the first and the last, there were in fact two orders of magnitude. And when you are first, 7 years after, you will be the last of the top 500. Okay. Now, things have changed. Between the first and the last one, almost 3 orders of magnitude, 700. Okay. And from the first to become the last, it is 15 years. What can we extract from that? Maybe a slowdown in investment, the fact that energy costs and makes decision-making different. A lot of things can be extracted from that. So I try to make an highlight. And this highlight I chose through the global power envelope of the number one, and the energy efficiency, and it's not green 500, it's the energy efficiency of the score at the top 500 divided by the declared power consumption. Okay? So you can see that in the years 2000, I think it was a Roadrunner, it was a teraflop. The facility was 3 megawatts. Okay? And energy efficiency, wow, 0.1 gigaflop. In fact, megaflop was a more appropriate scale. Okay, and then you have this for the first. I just did the math for the first because sometimes the second is better than the and so on. Okay, but the trend is there. So to lead in the years now, a power envelope close to 30 megawatts, an energy efficiency of 60 gigaflop per watt. Okay. So imagine the tremendous progress, and the progress is even more evident here. So the blue points here is energy efficiency. Okay, so we see a real breakthrough here, and this is related to the adoption of accelerators, GPU here. Okay, Fugaku was a nice try, but well, it is not the first, but it was at 40 megawatts. So here there is a great breakthrough. What this star, yellow, I related that to the growth of energy price over the world. So in the US, you see it's more comfortable than in Europe. But imagine, even for an American guy, American center, okay, he has to face an expense of 30 megawatt facility, okay, at an energy cost which is 3 times he had to handle in the year 2010. So the bill is almost 10 times more expensive, 10 times, and it is for the US. For Europe, by decency, I won't tell. It is a punishment. It is a punishment, and the punishment is just starting. Okay. So, well, cost energy is becoming a real subject, the subject, in fact. Okay. So, for large infrastructure, when you consider total cost of ownership, is purchasing and exploiting. And the ratio between OPEX and CAPEX is really changing. That means that the part of exploiting the machine is becoming more and more important comparing to the acquisition. So this is a game changer in decision making, really. Okay? So we need to consider now energy-aware performance optimization, and my 2 colleagues showed a real focus on energy, tools and stack, but also we have to also to consider lifetime strategies. Because if we keep a machine that is not efficient in terms of energy and in terms of cost, well, it's not a good decision and not a good use of money. Okay? So, mastering energy is a systemic challenge. It's from the floor to the ceiling, okay? You have to consider infrastructure, and on top you have the application. So infrastructure is choosing the good cooling technology, strategy, why not heat reuse, when possible, energy supply source, and so on. It's a great subject. Then it's about component and architecture. And here, EUPEX starts, okay? And then, in the other 4 blocks, that is what you presented, kind of virtuous, not virtuous, in fact, it's a constant loop of improving, keeping track of what is going on the machine, is an application doing a proper use of resources, and so on. So we have, during the lifetime of the machine, always figure out, do I use the machine in the most efficient way? Okay. So I will focus on two methods, two aspects that we have used agency for, yes, almost more than 10 years. The first is a total cost of ownership method for choosing a machine. And the second one is a recent study we have done. It's lifetime production, so it's about lifetime of the machine optimization, considering some parameter I will show. So first, TCO method. So don't be afraid. It's quite easy. So it has been used on machine Oxygen, on Adastra, on Janzé, and recently also on Alice Lecoq, okay, the Exascale machine. So the starting point is total cost of ownership. Purchase, maintenance, infrastructure, staff. Okay, this is quite okay. We can, by a rule of thumb, figure out. And then TCOE, mean total cost of ownership, focus on energy. This is composed of energy of compute, energy of disk, energy of CDU, with each time a PUE. And the object to make this measurement is the workload. So these colors are application. Okay? So we say to the candidate, okay, you have this bunch of application, this model, and you can, so there is here CPU and GPU. On Alice Lecoq, it was more GPU based, accelerated based. So this number of instances of codes, and the candidate is free to run it, but he has to minimize the time, the size of the machine, and also the power envelope. Okay, and this is measured. So the size of the machine, obviously, is not the final size, it's a smaller one. And then we make a comparison between the numbers we got by measuring the time of this Tetris, because it's an arrangement, and we make a comparison between what is the size of the benchmark machine comparing to the size of the machine that will be proposed. And this is a ratio. So the energy of compute of this object is multiplied by the number of times the size of the machine will be proposed. And we chose 5 years to pave the space and time. And then we have, at the end, the TCOB, which is what is the cost of my benchmark. And we choose the machine saying, okay, what is your cost? 120, 140, I choose 120. So, and it works. And what makes us think that it works is if we use HPL instead, the ranking is not the same. Because obviously we have not the same constraint and not the same profile. So this has been used, and so it's a bit a hell for candidates and integrators. I think I have a voodoo in my for that. They don't like it, but well, it's interesting. And the other aspect is, when should I replace my machine? So again, I put energy cost. The global power envelope increase per generation. Each time you increase a generation, the power envelope increase for the same price. Okay. The percentage of maintenance of a capex, obviously. The renewal technology rate, 2 years, 3 years, something like that. So we can make on an annual basis a mathematical object of a ratio. Okay, and then application speed up. So I will not enter this time into math. It's believe me. And I have two families of trend. The first is high range speed up of application, and the other one is average speed up of application. This is realistic, and it is quite going on, what is going on HPC environment. 1.6 to 2, and you can see that, okay, my optimal duration for keeping the machine is around 3-4 years. Okay, and if you have a very poor acceleration factor, well, just keep it, don't change, or change the application. Okay, and if you have skyrocketing acceleration, which could be a phantasm for HPC, but with AI, it is not the same story. So what we have to also to consider is that this must characterize the global acceleration of all the exploitation on the machine. So it's a very much averaged. But this is a key for making it. If you have a pure AI machine, change it on each generation. If you have an HPC machine, keep it 3-4 years, maybe 5. This is what the math says for the best use of money.
You should submit a paper in S1 theater.
You can tweak the thing and you will see the curve moving. But okay, I took some assumption and these are the math. So Exascale is no longer how fast, but how efficient. And I would add something. It is recorded, never mind. There was also a societal challenge. I mean, data centers are considered as nasty things that will drive humanity into hell. Okay. Okay. Putting ears on my brother-in-law on a data center. Is it useful? I don't know. For fun, for sure. An Exascale machine for science maybe has the hints to find, yes, breakthrough and way of progress and so on. So I would advocate to make this kind of tool differently considered as data centers. This is my message. And I would like to thank you for your attendance.